with another presentation still for making the concepts that are a little bit strange, a little bit unusual, more obvious to the excited students. So I'm just going to switch to his presentation. Let's welcome Jim Weaver from IBM.
Well, good afternoon, or it's afternoon here, I guess there as well. My name is Jim Weaver. Thanks, Adrian, for inviting me to speak, and I've been sitting in on the entire workshop and the entire day, and have found the content fascinating. I hope to then be able to follow that and give it justice. Basically, a lot of the things I'm going to say or that are things that you've already heard. So I'm going to be able to skip through some of those parts and really get to the meat of what I'd really like to show you. And what that is I'd like to essentially do a let's play video of a game that I created that very much is like Minecraft or Portal. And I've been using it to help high school, junior high, and college students get up to speed on quantum computing. So the name of the name of that game is SIGCSE Blocks, and if you look here at the bottom of the screen, you can see the link that you would go to get SIGCSE Blocks. It's just a URL qisk.it/blocks. If you go to that, then it goes to my GitHub page where there are instructions for installing it. There's these slides, the ones that you're looking at. These slides are linked here, and some other information. And a little bit about me. I'm a quantum developer advocate for IBM. I'm a Java champion. So for basically been a classical developer forever, and got bitten by the quantum computing bug about 4 years ago when I saw Vincent Cerf. He just talked about, he was on stage at a conference on a panel, and he mentioned something about Shor's algorithm, and I knew nothing about it. And I had to look at Wikipedia, check out what that was, found out about this new kind of computing where instead of using bits and bytes, you can use the quantum mechanical properties of the universe to compute. And so about 4 years ago, I took the red pill, and I'm seeing how far down this rabbit hole goes. I've written several books, mostly on Java and Raspberry Pi. Just released a new book called The Definitive Guide to Modern Java Clients with Java FX. And so typically, I go through an introduction to quantum computing. I try to help people to get up to speed on some of the quantum mechanics, but other people have already done that. They've talked about what a quantum computer is, why. There's been several Feynman quotes. We've talked about exponential growth. There's Peter Shor, Grover. We've talked about different quantum computing domains that are, especially in the near term, going to be very useful. Machine learning, chemistry being the killer app for quantum computing, the reason for being kind of thing that Dr. Feynman challenged us to do. Optimization, of course, and then because finance is essentially a multivariable optimization kind of problem where you've got lots of different variables in a portfolio, for example, that you have to model. It's really good for quantum computing. And so a lot of times what I'll do is go through a lab, a polarized filter lab, which I won't do here. One thing I am going to do, though, I'll stop very quickly because this is, you know, this has to do with educating people on quantum computing. One thing that I like to do is to help students get up to speed on quantum computing is in the context of Grumpy Cat. So you know that symbol on the right, that's a ket. It's part of Dirac notation, and it's just a quantum state. So what I tell people is that I've got this microscopic cat at home, and sometimes my cat's grumpy, sometimes my cat's happy, but I've never observed in between those two states. So that just uh, leads to the first axiom of quantum mechanics, which is the superposition principle that states that my cat can be in any combination of grumpy and happy. And uh, as we know, we can represent a quantum state on a Bloch sphere. Here, uh, we can we can also represent it on a two-dimensional plane. A two level state is essentially can be can be referenced or represented in a two-dimensional vector space here with amplitudes and measurement probabilities. And so my cat can be, for example, grumpy or happy, and this is how you would represent it. Or it can be in some kind of superposition between grumpy and happy, and here are the amplitudes. Then axiom 2 is unitary evolution. My cat can evolve from being grumpy to happy, and I can force that issue by running my cat through an X gate, for example. And with evolution, with unitary evolution, the gates, like the X gate, can be modeled as matrices. So this gate is an X gate. Here's a 2 by 2 matrix. And if I take grumpy cat, which is represented as 1 on the grumpy axis, 0 on the happy axis, and multiply them by this matrix, then a little trick that you probably all know about where you've got a one-hot vector and you're multiplying it by a matrix, you can take the row that the 1 is in and just pick out that column. And so when I multiply these two, this first column is what the answer is. So grumpy cat turned into happy cat with that matrix, that unitary matrix. Then we have Hadamard gates where we can put cats in equal superpositions. So there's an equal likelihood that it'll be happy and grumpy when I measure it. And here's the matrix for the Hadamard gate. And same deal, take a grumpy vector, pick out the first element here, the first column of the matrix, and then this is the result. So my grumpy cat, putting him through a Hadamard gate, is now in an equal superposition of grumpy and happy. By the way, if you have any questions as we're going through, please do signal to Adrian that you have a question, and then I will stop and take your question. The third axiom is measurement. The probability is the amplitude squared. So if we have my cat that is the coefficient grumpy is root of 1/3. The coefficient of happy is root of 2/3. When I observe my cat, there's a third probability that it'll be grumpy, a 2/3 probability that it'll be happy. And then if we have multiple cats, we've seen this as well. We just take the tensor product. So there's grumpy cat. We take the tensor product, which doubles the state space in this case. And now my cat, my grumpy composite state here can be represented by 1, 0, 0, 0. Same thing with grumpy and happy, only it's 0, 1, 0, 0. And then we could put them all together by putting cats into superpositions, by putting them through gates, and then measure it with various probabilities. There's another related phenomena with quantum mechanics that's very useful in quantum computing, and that's quantum entanglement. You've seen this before, and but I just want to illustrate it with cats. We have Alice and Bob, our cats. We have our circuit diagram. We run Alice through a Hadamard gate. She now is in equal superposition of grumpy and happy. We use a two qubit gate called a C0 gate, and now whenever Alice is happy, then Bob turns happy, and we end up with this what's called a Bell state. It's one of the maximally entangled states. I've just got a little cat bell there as a mnemonic device. But notice the only possibilities are either grumpy, grumpy, or happy, happy. And there are no other possibilities in this state. So therefore, when we measure, if we measure Bob happy, then Alice is happy. As a matter of fact, this works on any distance. So if Bob got in, or Alice got in on a spaceship, went to Venus, Bob got in a spaceship, went to Mars. If we observed Alice on Venus and she's happy, then there's a 100% probability that Bob would be happy. Conversely, if we measured Bob on Mars, he was grumpy, then Alice, 100% probability, is grumpy. And so now I'd like to go into the meat of of the presentation, and that is SIGCSE blocks and leveraging that to teach middle and high school students, as well as here just recently, I used SIGCSE blocks to help an ACM chapter in Northern Illinois University get up to speed on quantum computing, and so that's the crowd in the background, right before the presentation. I always take a selfie with my audience. In one workshop, it was for, I believe, 10 to 16-year-olds. This student, who is closer to 10 years old, I'm guessing, than 16, was actually the one that got through the puzzles, the Minecraft-based puzzles, the quickest, and I thought that was kind of cool. So I showed you the site where you can get at it at SIGCSE blocks, and there's some simple instructions for installing it. I've already done so, and so I'll skip that part. It's just like Minecraft. You get around the SIGCSE blocks world by using keys. Like if you're a gamer, you know intimately that W, A, S, and D will move you around, and there's other different kinds of controls you can use. And there's many different areas of the world when you're in world, and I'm going to show you some of those. But the main ones are going to be these portal-like puzzles where you go into escape rooms and you have to solve a quantum circuit in order to escape the room. So I'm going to go ahead and just go into game. And when you go in there, you can pick a world. When you first install it, you'll be creating a world, but it's very easy installation study instructions. So I'm just going to go into play game here. And when you get into the world, you start in the main room. And that main room has lots of different blocks that are each quantum gates and quantum operations. And before I go into the escape rooms, I'm just going to show you around a little bit. First of all, I'm going to go over to this minecart and maybe take a little tour. And we'll see that underground there's a bunch of quantum circuit puzzles down here that we'll be experiencing. There's also a quantum circuit garden over here with various levels of quantum circuits. I'm going to go ahead and fly over to another area real quick here. Here's actually one of the presenters, EJ, actually showed talked about quantum teleportation, and so here's a working example of quantum teleportation. I'm not going to focus there though. I'm going to go over here a little bit, and here's a cat sandbox, and this is a way for especially the younger students to be able to experience um, some of the quantum computing principles that you just saw in that presentation where I gave the introduction with cats. For example, over here is just an example of an X gate, and so they can right click here and do a measurement and see that every time grumpy cat turned into happy cat. Or over here, they can play with an H gate and experiment to see, well, sometimes he's grumpy, sometimes he's happy. And then over here is one where we've got the entanglement circuit, the Bell state, and these are continuations here. Those continue over to here. And we can see that when we measure that, then sometimes they're both happy, sometimes they're both grumpy. These are continuations of these wires. So it's just a resource. If you download that, it's a resource that you'll have to help students get up to speed on quantum computing, especially the younger ones. But where I'm going to focus the rest of my time then is in the portal-like escape rooms. So we'll land here, and to do that, what we'll do is go into this TARDIS. This TARDIS actually contains. If I go inside, there's actually a portal room. It's a portal hub. So when we go in there, we see lots of levels. I've got 2 of them built out completely. These blue portals are ones which you can jump into a room, and then the yellow, orange, or yellow portals, you can jump back out. So I'm going to go ahead and jump into room 1 here. And then we see, if you've ever played Portal, you know that when you get into a room, you need to kind of study things and figure out what's going on to try to figure out how to escape the room. And there's clues in here, like in the upper left-hand corner. Maybe it's hard to see, but this Professor Q over here that's behind this protective glass, she is telling us, she's greeting us saying, "Hello, test subject 576. I mean, esteemed colleague. My name is Professor Q, and I'm standing behind this blast glass because we're going to try an experiment. Hopefully it won't vaporize you or scramble your molecules. For this experiment, change the quantum state of the circuit from 0 to the state shown on the wall." So we look around a little bit, we see, okay, there's a state shown on the wall, it's 1. We also see kind of a representation of that state, indicating the liquid level of this block here, indicating the probability that state will be chosen when I measure. And then this symbol right here just means to get out of this room, which is that symbol, corresponds to that symbol pointing to that door. To get out of this room, make that circuit have this state. So we look around, well, how can I do that? Well, I've got a chest here. I'll right click on the chest. I see an X gate. You all know where this is going, right? So I right click on this spot right here, which puts an X gate on the circuit, on that wire. It changes the 0 going in to a 1. Here's our state vector, and here is the measurement probability then that a 1 would be selected if I measured it. Also here is the familiar block sphere, which has its state down at the South Pole, which is the 1 axis. As a review, here's a block sphere, and there's a link to this site here where you can play with a 3D block sphere And we can see, well, if I start out with a 0, I apply an X gate, then it's going to be 1 or Hadamard gate, etc. So now back to in-game. Since I solved the puzzle, the door opened, and now I go to the next puzzle. Look around. The quantum state I need is 1, 0. And Professor Q up in the upper left-hand corner is saying, please make its, we're going to do a multi-qubit thing. Please make its quantum state match the one on the wall. And so we look at 1, 0. We see that the color of the first qubit is magenta. The second one is yellow, which maps out to these two. So what's in my chest? We know it's going to be an X gate, right? So we pull out the X gate. Which wire do we put that X gate on? It's just like cutting a wire to a bomb, right? I don't want to cut the wrong one. There's a clue, a visual clue. Let's put it on the magenta wire because that's the one that turns 1. And turns out that at least in SIGCSE, by the way, we're using a SIGCSE simulator for this. In SIGCSE, the most significant quantum bit is the bottom wire. And so this state is 1, 0. We look at the representation here, we see 100% probability that if we measure, it's going to be 1, 0. We also see our block spheres at the south pole meaning 1, north pole meaning 0. And if we do a measurement by right-clicking these things, we can see that it's always going to measure 1, 0. So now we've solved that. Let's find the door, go to the next one. A little bit more of the same here, only we're going to be using 3 qubits. Professor Q's telling us that. And we need 0, 1, 1, no surprise. We're going to put an X gate there, X gate there. That solves the puzzle. A little bit harder to find the door this time, but it's behind here. So now we're going to get out of classical territory and into more quantum mechanical territory. It says you're catching on quickly. You're also noticing that there are 2 to the n power of basis states, where n is the number of wires. Here, back on the last one, there were 3 wires, so 8 basis states, 0, 0, 0 through 1, 1, 1 were necessary. Now this room, the one we're in, this is where Schrodinger's cat starts getting nervous. It wants us to put the qubit in an equal superposition of dead or alive, I mean 1 and 0. So we go over here, and what do you think's in this chest? I'm going to guess it's a Hadamard gate. So we'll pull that out and put the Hadamard gate right here. I've got to wield the Hadamard gate first. There's our Hadamard gate. We've solved it because the block turns gold. Reviewing what the objectives of the puzzle were in this room, we need an equal superposition of the 2 equal superposition of for this qubit of 0 of measuring 0 and 1. There we've got the liquid is half and half. These arrows we'll talk about those in a little bit, but EJ's already talked about them in his circle diagrams. This is just a different way of representing things, and it has to do with the phase. So here we are. We notice that it's equal superposition, and as other speakers have talked about, that particular state has another way of referring to it, and that is called a plus state. So as others have mentioned, anywhere on this equator of the block sphere is an equal superposition. And because there's an equal probability of measuring 1 or 0. Now the one on the front of the sphere here is called the plus state. The one on the back of the sphere is called the minus state. Okay. So now we've made the plus state, and we can go through the door. Our next challenge is to get to the minus state. And so Professor Q is saying, let's visit the back side of the block sphere in a state commonly known as minus, where measurements resulting in 0 or 1 are also equally likely. So if we look at the Dirac notation on the wall, we see that instead of, square root of half 0 plus square root of half 1, it's square root of half 0 minus square root of half 1. And that minus is telling us that the phase is a pi rotation, and we are on the minus side. So how do we get there? Well, what gates do we have to get there? Let's see, we have an X gate and we have an H gate. So how would we get there with an X gate and an H gate? Well, I could naively try to do an X gate and then an H gate, and that works because the X gate, going over to our block sphere, if we started out here, the X gate takes us to the South Pole, to the bottom, and then the Hadamard gate takes us back to the back of the block sphere. If we had tried that the other way around, then that wouldn't have worked. So we say that those operations don't commute, right? You can't switch those around. The reason why that doesn't work, it didn't take us anywhere, or it didn't take us to the back of the block sphere, because if we look at the block sphere here and we try that exact same operation, go back to the beginning here, we'll try an H. What does the H do? It puts us at the plus. And then we apply an X. What does the X do? X rotates around the X axis, which had no effect here. So to actually solve that puzzle, we have to do it in the correct order. So now we find out that the next puzzle is we need to get to the same place on the back of the block sphere, but the gates we have are different. This time we have a Hadamard gate and a Z rotation gate. So we know that if we're in this state, at the 0 state, if we do a Z rotation, that's going to have no effect, right? I could rotate all I want to on the Z axis, and it's going to stay in place. So we know that we have to apply the Hadamard gate, which gets us to the plus position, followed by the Z gate, which is going to rotate around the Z axis and get us back to the right place. And we notice that the blocks here and here, we see that the arrows are pointing to each other. They're 180 degrees or pi out of phase. And so that's why we see we're at the back of the block sphere, and we've got a little bit of quantum interference going on, right? That we use with quantum algorithms. Okay, so now we're done with that puzzle, and let's go on to the next one. Well, we see the challenge here is we want to get to this quantum state, and Professor Q is hinting to us, that looks like a complicated quantum state, but if you take it one qubit at a time, one wire at a time, you ought to be able to figure this thing out. So let's see what we've got to work with. Now we've got this chest that has an X and an H. And then if we look at the quantum state we want half the time we want magenta to be 0, and half the time we want it to be 1, magenta being the lower one. So what gate would we use there? Well, we'd use an H gate. The second wire is always 0. It starts out at 0. We don't have to do anything there. The third wire is always 1. So we need an X gate there. So now we've got that state now, 0, 0, 1, half probability, and 1, 0, 1, half probability. So we're good. We can go through to the next one. And the challenge there then is to put these two wires and its four basis states, more importantly, into equal superpositions to where with each of them, there's a 1/4 probability of measuring each of the different states. So how do we do that? Well, you know from the previous presenters that there's going to be a Hadamard block in there, and that we're going to put those into equal superpositions by just applying two Hadamard gates. Okay, so that was relatively easy. Let's see, we'll try to find the door, which is in the back of this thing. And then now what's the next challenge? Well, the next challenge is to put 8 basis states into equal superpositions. Well, I know you can guess how to do that, right? You just take the H and then, but before I apply them, I want to call your attention to this notation here. So it's direct notation, but we're using a summation notation as well, to where we're saying we want the square root of 1/8 amplitude for all of the basis states. And so we're just using that summation notation to do that. And so we'll put the Hadamard gate in all 3 of them. We see equal probabilities of measurement. And now we will go to the next one. So now we've got a special state. Now we've already visited this state several times today, and that is a Bell state. There are 4 Bell states, and we're going to cover them all. This first one is, when people say Bell state, they usually mean this one, right? This is one of the 4 maximally entangled states. This one is called phi plus, and it's the one we've been dealing with mostly today. So if I look in the chest, no surprise, we've got an X gate and a Hadamard gate, and then we've got this this control tool. And to work with that control tool, what we'll do is first is place an X gate, and then we'll use the control tool, and I'll left click on the X gate, and that will turn that X gate into a C0 gate. And then I'll take the H gate, wield it here, and that makes a Hadamard gate, or that places the Hadamard gate, which then makes our Bell state. Now notice that the block spheres are showing question marks. And that just symbolizes that others have said here that, that when you have entanglement, you can no longer express the state as a product, right? So the states of these qubits are really undefined. And so here's the state on the wall, the half probability of 0, 0, half probability of 1, 1. Both the arrows are pointing to the right. This is the phi plus state. And so now we can leave. The next one is called the phi minus state. And that is characterized by a pi rotation on the phase. And so to make that, then, we'll use the same blocks. We'll just use them in a little bit different way. So we'll wield an X gate here. We'll turn that into a C0 gate by left clicking it with the control tool. We'll use our Hadamard gate, and that gives us our phi plus state. And then we'll just take an X gate here and turn it into a phi minus, sorry, wrong place, into a phi minus state. Okay. Which is also one of the 4 maximally entangled Bell states. And so now we've got another Bell state, but this is called a singlet state. Notice that we have 0, 1 here and 1, 0 here. And so what happens is when you measure one of the qubits, the other is guaranteed to be the opposite state. That's called a psi, PSI, psi plus state. So to make that, we use the same gates, a Hadamard, going to need a C0 gate, and we'll be using an X gate as well. So let's put our X gate here, and turn it into a C0. We'll put a Hadamard here, and then we'll put an X gate here, and then that made our singlet state, our psi plus state. And then the last of the 4 maximally entangled states is the psi minus state. Now for that, we're going to add a gate, the Z gate. So we'll place, as usual, we'll place an X gate, turn it into a C0, place a Hadamard, and then we're going to place an X gate here like we did with the phi minus state, or the psi plus state. But then we're going to place a Z gate to handle that phase. And so now we have a singlet state in which the phase is pi out of phase. Okay. So now we've got 3 qubits that we want to be entangled to where the only 2 possibilities are 0, 0, 0 and 1, 1, 1. And that's called the GHZ gate, which is named after 3 physicists whose names begin with G, H, and Z. And so some of you know already how to make one of those. Some of you can kind of intuit how to make one of those based upon what we've seen already. But we'll throw a Hadamard gate up there. We'll put an X gate up there and make a control out of it. And then we'll put another X gate here. And we'll control there. And then that makes it so that the only 2 possibilities are 0, 0, 0 and 1, 1, 1 through this entanglement. And of course, that's not the only way you could make it, right? You could make it like this. And that would make that state. We could bring the control up one more. Number of ways to make it. The important thing is the resultant state vector matching what you want. So now we're going to play with some rotations. So here we go into this room. We see that we want a state that is this 0.85 probability that we measure 0, 0.15 probability that we measure 1, and in addition to that, we want the rotations to be this on the 1. We want the relative rotation to be pi over 2, which is a 90-degree rotation. But that's a 90-degree phase rotation. When we see this e to the I, that's just notation for some kind of rotation on the phase. And here, it's a pi over 2 rotation on the phase, which is 90 degrees. So to get that, we're going to get a couple of new blocks. So one of the blocks is a Y, an RY, a rotational Y block. So we'll place that. And then one of them is a rotational Z block. So we'll place that. Now this tool will rotate whatever rotational gate it is. And so I'm just going to rotate it by about that much. And then I'm going to rotate the Z gate to where it it goes around the z-axis and to where I can see this arrow now point up to where this one is pointing up. And so now we have this state where the probabilities match up with the ones on the wall. And if I look at our block sphere representation, I could make this a little clearer in a block sphere that has better resolution by hitting the RY here until it gets to 85% probability or 0.85 probability, and then rotating it on the z-axis until I get to a pi over 2 rotation. And so that's the same state as I desired here, and as that I'm trying to represent there. And so then the last puzzle on this level, in this fundamental level, is one in which we're going to set up the initial state in an equal superposition. Other presenters have talked about how quantum algorithms tend to start out with the qubits, all the qubits having Hadamard gates, so that you're actually starting out in an equal superposition, and then you do rotations to express your problem and express the algorithm, and then you use Hadamard gates to get back into the computational basis. So we're going to do that same thing here. So we're going to get into the chest. We see we have Hadamard gates and rotational gate. And so I'm going to start out by putting a couple of H gates there, a couple of H gates there, and we'll do some rotations on the z-axis, some phase rotations, until I get what we want here. And so that state that we want here is actually an equal superposition of all 4 basis states, but the phases are different, what I want. Okay, so I'm going to take my RZ gate, put each one of those there, and then here I can left click or right click and make this rotate until I want it to, until it's where I want it to be. Maybe I want it to be there. And then, let's see, we'll rotate this one until it matches what's on the wall. So we see that the phases and the amplitudes are all the same as what's on the wall. And so that's, as EJ said and others have said, you know, we're starting out with Hadamard gates. We're using rotational gates to change the phases, and then we're using Hadamard gates then to change to changing the changes in phase to changes in amplitude, which then affects the probability of measurement. Okay, so now that was the last puzzle in the fundamental level. And so now I'd like to take you to the second level. And this is more of a logic level. So here, the problems are expressed usually as logic expressions, Boolean satisfiability expressions, if you will. And so the first one is we want whatever's on the top wire, whatever it starts out with here, to persist over here. And then we want the bottom wire, B, for its value to end up with as A, X OR B. XOR is exclusive OR. So if A and B are both true, then we would want, if they're both 1, then we would want B to be false, et cetera. And we'll go ahead and work through that. So here's what we have to work with. So I'm going to make Some of you may recognize that as a C-NOT gate. I'm just going to make a C-NOT gate. There's a couple ways to think about a C-NOT gate. One is if I go in and if I start out, let's say, with this top wire being 1, here I've just changed it from 0 to 1. I'm just forcing the issue to make it a 1. Then if that's 1, then this one flips, right? So that C-NOT gate, you can think of it as if the top wire is 1, if the control wire is 1, then it flips the bottom one. And so sure enough, that's taking a 0, 0 and making it into a 1, 1. So you can think of it that way. Another way you can think of it is as an XOR. And so here, A is 1, B is 0, and that fits, that meets the condition of an exclusive OR, which is one or the other is on, but not both. And so therefore, B should reflect that that condition is true. B is 1. But if I made them both 1, for example, that doesn't fit the exclusive OR. And so B, which is that bottom wire, should end up being 0, which it is. And if I did measurements, then we see that B is always 0. Here we've got exclusive OR, so B should always be 1. So that's that's one of the simplest of the logic gates. And then I should mention that that as I go through this level, if you read EJ and et al.'s book, you'll notice a lot of these constructs in there in the amplitude and phase logic portions of his book. So now this one, A stays the same, and then B we want to be not A XOR B. So no surprise, we would just take the same kinds of blocks here. But since we want not X or B, we'll throw a NOT gate there. And so this circuit, this quantum circuit, expresses this this Boolean satisfiability problem, in which you tried to, in which you are would try to find values of A and B that satisfy this expression. Okay. So then, sorry. So then the next problem is C is A and B. So others have mentioned this thing called a Toffoli gate. And so we can make a Toffoli gate using these gates here, using the X and the control tool. Here we'll take the X and then we'll apply the control tool, hit it a couple of times. And then I'm going to hit this a special key. The special key you can see if you go into if you hit escape and then go to change keys, you can see that the special key on my keyboard is X on my installation. So I'm just going to hit X on my keyboard and then hit Shift, and that will place a second control wire, or control point on my Toffoli gate here. And so then A and B should always result in or C should always result in A and B with the Toffoli gate. So 0 and 0, that's 0. But if I said 1 and 0, logically, it still should be 0. And we notice that the 0 bit, or the magenta bit, the most significant qubit, is still 0. But if they're both 1, we see that over here that it ends up being 1. Now the neat thing about the quantum computing, because this is all classical, but the neat thing is that that I'm going to show you in a little bit is that you can compute this in superposition and find out all the answers at the same time, you know, all the combinations at the same time. So let's go to the next room. Okay, so now we have A, or C is A, not and B. And so that's the same kind of thing, only, so we'll use the Toffoli gate. But we'll put a not at the end. And so now C is not A and B. Or another way of saying that is C is A NAND B. And then the next one is we need an OR gate. So A is going to stay A, B is going to stay B, but we want C to be A or B. And so if you look in EJ's book, you'll see that a way to make an OR gate is to make a Toffoli gate, and then you negate the inputs. So an OR gate is like a negated NAND gate. So here we go. So we'll negate the inputs, and as others have said, you need to clean up after yourself. You need to uncompute things, right? Because when you're entangling things, you don't want to leave leave your qubits in bad states. When you don't need to change the value of the qubit, like on these inputs, then what we do is we uncompute and leave them the way we found them. And then we're going to negate the result there. And so then that is an OR. So to prove that, if we put there, if we put a 1 at this top, at the A position, then we see that A or B should result in C being 1, which is the case. If neither one of them is true, we see that C, this bottom wire, C is 0. But if any of them are true, then C is always going to be true. So then we go to the next room. We want NOR, C to be A, not OR B. And so that's a similar kind of thing, except for we're going to negate the output. So here we say so that would be not OR. And I'll go to the next one here. So then here we have A goes to A, B goes to B. We want C to be not A and B. So remember that we have the Toffoli gate which is the AND gate. but then to get the not A and B, I'll say not A, so the precedence would be not A. It applies the not to the A first and then and B. So to do that, we'll not the A, and then we'll uncompute it. So this is not A and B. And so anytime we have not A and B, this should be, this magenta qubit should be 1. So here we have, let's do that. Let's have a not A and B. Well, here we have a not A, but in order to have a B, we need to force that to 1. And so now C is not A and B. So C is true. Right? So we can do these like this, right? We can set up our logic gates. Like, for example, if our satisfiability problem was, show me all the combinations that in which this expression is satisfied, this not A and B expression is satisfied, we could try all of the different combinations to figure out which ones make the magenta bit a 1. But that's, when we get up to, if you had 20 qubits here, you'd have to check 2 to the 20th power of combinations to see which ones work for your satisfiability expression. And so that's the point of the next room. The point of the next room is do the same thing, use the same logic, but compute in equal superpositions. And we'll see the magical results. When I say magical, I mean just quantum mechanical things that are enabled by a quantum mechanical phenomenon that seem magical. They're just part of the way nature works. But I'm going to go ahead and make that same gate there, that not and gate. That's the same gate. But instead of throwing conditions one at a time to it, like checking, does that one satisfy it? Does this one satisfy it? Yeah, I guess that one does. Does this one satisfy it? Instead of doing all that, what I can do is I can let the quantum mechanical properties of nature do it. So I will just compute in equal superpositions. And now it's showing me all of the combinations, all the valid combinations. So it's showing me that 0 for this Boolean satisfiability expression, if 0 and 0 are not the right answer, 1, 0 is not the right answer, 1, 1 is not the right answer, 0, 1 is the right answer. So those are the valid combinations and the right answer. The only problem is that although nature knows the answer, we can't know the answer because notice that all the probabilities are the same. So if we try to measure it, we just get our equal distribution. We don't have anything that we can use to determine, to know what nature knows. And so now we, and I see that I'm out of time, Adrian.
Yeah, a little bit.
Yeah, I'm out of time. So anyway, that's Qiskit blocks, and so next step would be to go in and download it, play with it, and continue on with those levels, and teach your students how to use it in a format that they already love to use, which is like Minecraft. So thank you very much.
Yeah, it was excellent, and maybe we have time for one question. We also need to give people a break, a little bit of a break, and then we'll come back for EJ. He will talk about the anatomy of a photonic quantum processing unit. So a book for a question?
If you could say the question a little bit louder, I'd appreciate that.
So when you started, I think you said you'd done this with a group of kids. What were their backgrounds? Did they had some computer science stuff, or were they coming in pretty raw, or what?
Oh, okay. Yeah. Well, so I've done this workshop several times with several groups of kids, and some had no background with it other than they had done some programming. Some had one of the high schools I did this with was had some more advanced programming courses. None of them had had any you know any physics or quantum physics kinds of backgrounds. I find during these workshops, the less of a background, there's no surprise here, but the less of a background they have in programming and in areas and in math, then the higher the ratio of mentors I need in class. So, maybe if I have 20 kids in class, based upon their background, it may be nice to have maybe 4 or 5 mentors that can walk around and help answer questions and help kind of guide them. Some classes, though, they maybe require maybe 2 mentors out of 20. It just depends.
Okay, so I think you said that you always take a selfie with your audience. I just sent you a selfie that you took. You on the computer.
Thank you.
You on the computer, and then everybody else behind you. It was
That's
a really
awesome.
nice presentation. Thank you so much. 5 minute break.
Thank
We'll come back. Sorry, EJ. In 5 minutes for EJ's presentation. Thank you.
Okay, thank you.
No worries at all. I think I can make up some time on the next one.